Let's talk about paracetamol. It is, without a doubt, one of the most widely used drugs on the entire planet. I mean, chances are you've got some sitting in your medicine cabinet right now. But the story of how this super common pill actually works, well, it's anything but ordinary. In fact, for more than 100 years, it was a complete and utter mystery. Think about it. You get a headache, you top a pill, and pretty soon the pain just fades away. It feels so simple, right? But for the longest time, the actual science behind that relief was one of pharmacology's biggest puzzles, a genuine mystery that we're only just now starting to solve. And hey, before we dive any deeper, let's get one thing straight. You might hear it called paracetamol, which is common in places like Europe and Australia, or you might know it as acetaminophen, the name used in the United States. Just know you're talking about the exact same medicine. Two names, one very, very familiar drug.
Yeah, you heard that right. Even though we've been using it to treat pain and fevers since the late 1800s, scientists were totally stumped. Everyone agreed it worked. That part was obvious, but nobody could say for sure how. So today, we're going on a little scientific detective journey. We're going to look at the original theory, uncover the absolutely groundbreaking discovery that changed everything, and explore why this hidden story really matters for your health. All right, first up, let's look at what scientists believed for decades. For the longest time, the prevailing wisdom was that paracetamol's magic all happened in one specific place, your central nervous system. The theory basically went like this. Paracetamol travels up to your brain and your spinal cord, and that's where it gets to work. This made it fundamentally different from drugs like ibuprofen, which we know have strong anti-inflammatory effects all over the body. No, paracetamol's action was thought to be almost entirely, well, central, all in your head, so to speak. The main suspects here were these things called cyclooxygenase enzymes, or COX for short. Now, these enzymes are key players in creating the signals that tell your brain you're in pain. The only problem, researchers could never actually agree on which COX enzyme paracetamol was targeting. Was it COX-1, COX-2? Some even suggested a mysterious third one, COX-3. The data was all over the place, and honestly, the mystery just got deeper. But then, a breakthrough. A team of researchers at the Hebrew University of Jerusalem published a study that completely rewrote the rulebook. It basically turned decades of scientific consensus completely on its head. The lead researcher on that study, Professor Alexander bin Stock, really put it perfectly. This wasn't just some small update to the old theory. No way. This was a fundamental shift in our entire understanding of how this incredibly common painkiller actually does its job. So just think about that. After decades of scientists focusing only on the brain, this landmark study revealed that a huge part of the story was happening somewhere else entirely. It was happening out in what we call the peripheral nerves, right where the pain signal actually begins. And here it is, the crucial piece of the puzzle. It turns out it's not actually paracetamol itself that's doing all the heavy lifting. Instead, your body takes it and metabolizes it, creating a totally different compound called AM404. And this molecule, AM404, is the real key to its pain-relieving power. What this amazing discovery showed is that paracetamol doesn't just stop the brain from hearing a pain signal. It actually stops the signal from ever being sent in the first place. It nips it right in the bud. So here's the news story of how it really works. After you swallow a pill, your body creates this AM404 stuff right where it's needed most, at the nerve endings that are sensing the pain. AM404 then acts like a bouncer at a club door, blocking the sodium channels that the nerve needs to fire off a pain signal. The message is basically silenced at its source. It never even gets a chance to leave the station. So let's just put these two theories side by side for a second. We went from thinking it was all about the brain playing defense, intercepting a message, to now knowing it's all about a metabolite playing offense out in the body, preventing the message from ever being sent. It's a total paradigm shift. But you know, this new understanding of its power brings us to a really critical point: safety. Because while paracetamol is remarkably safe when you take the correct dose, it can be extremely dangerous if you take too much. The key issue here is something called a narrow therapeutic window, and that's just a fancy way of saying the difference between a safe, effective dose and a toxic one is actually surprisingly small. An overdose is incredibly toxic to the liver, and it can cause serious, sometimes permanent damage. So what's actually happening inside your body during an overdose?
Well, normally, your liver has a system to neutralize a toxic byproduct of paracetamol called NAPQ, but an overdose just completely overwhelms that system. The NAPQ builds up to dangerous levels and it starts attacking and destroying liver cells. This damage can be catastrophic and, in some cases, even fatal. Thankfully, there's some really good news here. There's a very effective antidote called N-acetylcysteine, or NAC. When it's given in time, it helps the liver replenish its defenses and get rid of that toxic NAPQI. For massive overdoses, where the risk is just off the charts, doctors will even use a special double-dose regimen to counteract that severe toxicity.
So, what's the bottom line here? What should we take away from all this? Well, we now know that one of our most common medicines works in a truly revolutionary way, stopping pain right at the source. But this incredible new insight comes with a crucial responsibility. We have to have a deep respect for the drug's power and remember the absolute importance of using it only as directed.
And that brings us to one final, really exciting question. Now that we understand the true mechanism of AM404, could we use that knowledge to design a whole new generation of drugs? Medicines that are even more targeted, more precise, and maybe, just maybe, even safer than the familiar painkiller we all thought we knew so well. Now that is a question that could genuinely shape the future of pain relief.